Okay, it is now the appointed hour. So we were blessed with a 3-day weekend, which is nice. We only have, at least for this class, only have one real day of work. So, does anybody have any questions about anything before we start? Does anybody have any Pearson issues still? What's your issue?
I just can't open the book. It took me like 2 hours to register.
Oh. It's 2 hours, you'll never get back. Did you fill out a customer service request?
I'll check the
Yeah. But what I negotiated with Pearson, did you guys get my announcements? So, did you get the picture of the otter? Okay. So, you have to go to Pearson customer support and fill out the form and get a reference number. And if they don't help you in a day, write me and I'll escalate it for them. Well, for you. So that's what I negotiated with them, because it's just like you guys are taking too long, and like I need someone to talk to, and they said we can't do anything about the complaint number. So, anyways. Okay, so this is where we left off with the idea of significant figures. Okay, you can see this. Where is it? I have an inner ear infection, so everything's a little fuzzy. Is that clear? Yeah. Okay. So if I seem like I'm drunk, I'm not. I'm actually just dizzy. Okay. So sig figs, and the idea of significant figures, or sig figs frequently referred to, it tells you how well you know something. So here are the rules. Non-zeros are significant. Interior zeros are significant. Leading zeros are not significant. Trailing zeros are categorized. So after a decimal point are significant. Before a decimal point are significant. And after trailing zeros before an implied decimal point are ambiguous and should be avoided unless you're using it should be using scientific notation. And some books do something like this. So like if it's 10,000, it'll put a decimal point at the end there to imply that these zeros are significant. And then we have exact numbers that have the infinite number as sig figs. So things like I have 2 hands. It's not 2.0, it's not 2.00, it's 2 with infinity as far as the sig figs. I'm really sure that I have 2 hands, at least at this moment. I hope that doesn't change. So, how are we doing? Any questions? Okay, how many sig figs in each number? So, for A here, we have 4, 4, 5. These are non-zero numbers. They're definitely significant. Then we have a 0 after that. Since it's after the decimal point, there are 4 sig figs in that. So, questions? Okay, so then we have interior zeros. So those are significant, and we have 2 numbers at the end. There are 5 sig figs for this number here. So 10 decimeters equals 1 meter. This is an exact number. 10 decimeters does in fact equal a meter. There are an infinite number of sig figs in this. And 1 times 10 to the 5th seconds. So this is scientific notation. You have these 3 here. So these have 4 sig figs associated with this number. So the 1 and then the 3 trailing zeros. And these zeros are not significant. This has 1 sig fig. And 10,000 meters, this is ambiguous. This is 1, but this is kind of an unknown. You should treat it like it has 1 sig fig. So, questions so far? Okay. Now, let's look at in calculations. And the general rule is you go for the lowest number. So for multiplication division, you look at the number that has the lowest number of sig figs, and you round off at the end. So if for these calculations here, I guess for this calculation here, so 1.052, 4 sig figs times 5 sig figs times 2 sig figs, and you get an answer. You round off the answer at the end. So don't round these all up to 2 sig figs. Say, oh, this is 1.052. If it's 2 sig figs, I'll just say it's 1. And 12.5 up to 13. So, and then do it that way. You get what's called a truncation error. Truncation means you chop things off. So that's is a way to get error, round at the end. So same thing here, 3 sig figs at the end. Now for addition and subtraction, you can only go to where you know the your lowest value. So for these numbers here, notice that this one goes to the thousandths, this one goes to the hundredths, this one goes to the 10,000ths, but you're limited by the hundredths place. So you really only know, you're only certain to that 100ths place. Same thing with this one here. You know the tenths place, this one's to the thousandths, but you're limited by the tenths, so you round up to the tenths place, or round down to the hundredths place here. So another thing with rounding up and down rules, there's two schools for this. One of it, the most common one is that you always round up, so 0.5 always rounds up to the next whole number. Some places have 0.5 round to the nearest even number, so that way it's a split thing. So like if it's 1.5, it would round to 2. If it's let's see here. So what are we rounding down? 9.5. No, that we round up to 10. Shoot. What am I saying? Round up to. I guess I've never done it. I guess it. Well, let me think. Oh, if it's 8.5, then it would round down to 8. So, but this class we round up. We're thinking positive. Okay. And then the rounding. Okay, this is just further rules. Rounding, round at the end, and then and don't round in the middle. Okay. All right, so let's do some examples here. So first one here, perform this calculation, and if you do these calculations, one thing to note though, when you do these calculations, also as a teacher, this is my 14th year teaching, the most common mistake by far that students do in any circumstance is order of operations. So order of operations. It is always left to right, and first is when you have someone in parentheses. Parentheses happen first. Second are logs and exponents. Third is multiplication and division. That's a multiplication sign. It's an ugly star. And fourth is addition and subtraction. Always left to right. And calculators and smartphones, our smartphones have become our calculators. They're smartphones, but they rely on a smart user. They can only do what they're told. So you have to make sure that you tell it to do the right thing, otherwise you get the wrong answer. And that is, like I said, by far the most common mistake is order of operations. And I mean, you know, like as a student, don't get the easy concept wrong, get the hard concepts wrong. If you do everything right and you just do a calculator error at the end, then come on. You know, that's gotta be frustrating. That's frustrating for everybody. Okay, so number A here is easy. It's just all multiplication left to right. And what's also nice about these, so they do commute, so it doesn't matter what order you do it in. And if you put these all into your handy dandy calculator, you will get 3.4555. Okay, and now you gotta look to see what the lowest number of sig figs is. So this one has 3, this one has 4, this one has 5. You have to go to 3 sig figs. So this is going to be 3.50. So, questions with this one? Oh, wait a second. Did I write the wrong number down? Oh, I did. Shoot. I'm following the book. Sorry about that. That would be an odd thing. This is 0.65219. I blame it on my ear infection. Instead of 3 sig figs, it's 0.652. Questions out that I can copy the book properly? Okay, so B, I'll write this one out, 0.355105.1 minus 100.5820. So, and I even put the line here, so you only know to the 10th place there, and if you do that subtraction, you get 4.8730. And since you only know to the 10th place, you round up then to 4.9 to get your proper answer. Questions with this one? So for part C, you have to do this part first, and that's in the parentheses. Doing this part first, you get 0.3455, and the thing is that you're only sure but how many sig figs does this answer have? It only has 2, because you're only sure. Actually, let me use a highlighter. That might be easier. You're only sure for these to the 10th place. So this answer that you get really only has 2 sig figs. And since it's best to do the calculations and round at the end, you keep on going. And what you find out with this one is that this is 52.79904. And so you round to 2 sig figs. This equals 53. So do you see this one? So you do the parentheses first, but that subtraction, you go from 5 sig figs to 2 sig figs. So then at your end calculation, you only know the answer to 2 sig figs. And the last one, the parentheses don't matter because you would do that first anyways. But if you run the calculation all out, you end up getting, I mean, you can just throw this straight in your calculator. You get 0.104. Oh, wait a second. Again, I can't read the book. Is my vision that blurry? I'm glad I made it to work today. Jeez. Oh, actually, this is a little trickier. This one is even trickier because this quantity here in the middle, this is 8. This quantity here is it's 8.162, and then you subtract 8.02. So that means you only know the answer to the hundredths place. So wait a second. So you get 0.14142. I'm misunderstanding what the book is doing here. 0.1. It's rounding up to 0.1. Oh, I see, because this one you only know. Okay. Sorry, I was looking at this one. This one is kind of confusing. Okay. So you do this one here first, and you get 8.162, but this number here only has 2 sig figs because of the 0.55. So you really have 2 sig figs here, and you subtract that, and you come to here, and since you only know this one down to the 10th place, this answer here, you only know to the 10th place. And this is even more confusing because if you round this one to 8 if you round this one up, actually no, I guess you would be fine there. Yeah. Okay. But this one's really confusing. So, questions with this one? You normally won't get something this confusing. This is kind of an odd case. So let me explain that again in case you missed it, in case I missed it. You do this calculation first to get 8.162. This number has 2 sig figs because of this number here. So this number has 2 sig figs. You do the subtraction, and so since you only are sure to the 10th place, and when you do the subtraction, you have to give the answer in the 10th place. So questions with that one? Okay. All right, so next concept, general problem solving. So I'm pretty sure, I think I asked this before, no one's taking this course for your own benefit, right? You're not saying, boy, I can't wait to take general chemistry. This is my favorite class. And hopefully it is your favorite class, but most students hate chemistry. And I love chemistry, but I'm also, born and bred to be a chemist. So let's say you see me 10 years from now, and you're like, you know what? I know the solubility rules so well. I think about the molecular mass of water all the time. So glad I took your class. I really feel like what I'm teaching is problem solving. So when you hope, then that's one of the main points I'm trying to have you come to this class. If you leave the class, like, okay, I know how to solve problems. And I mean, I know you obviously know how to solve problems before you came here, but there's a certain way of doing it, at least, especially in Chemistry 161. When you get a problem, you have to attack it. So I guess I'm thinking very violently. Whenever I see a problem, like, all right, let's attack this problem. Let's see what's going on. I look at the problem and I think, okay, what is it they're asking? What do I know? I got to figure out where to go with this, and I got to solve it. And then after I solve it, does this make sense? So, and this is what the book says. So you start off by sorting it. Let's take the problem. Look to see what the problem is giving you and then what it's asking for. And then you think, okay, how do I get there? Okay, now let's do it. Let's do it. And does this answer make sense? And the last part there, many people skip that step. So that can save you a lot of time. So here's 2 examples. And I would solve it differently than the book does. I remember this one. So convert 1.76 yards to centimeters. So you're sorting. What do we know? We know that we have 1.76 yards, and we need to go to centimeters. So how do we solve this problem? Well, obviously somehow we have to convert between yards and centimeters. So we got to look up the conversion. So let's do that. And then we got to solve it. So start off with, and this is called dimensional analysis, 1.76 yards. Let's do yards, not years, but yards. So 1.76 yards. And there are certain relations here. So 1 meter is 1.094 yards. How do you YD for yards? That's what the book is doing. And then we have 100 centimeters to a meter. And if you look to see what they're doing, what's going on here, you're multiplying it by 1 twice. So you have 1.76 yards, and a meter is in fact 1.094 yards. So you're multiplying it by 1. 100 centimeters is a meter. Oh, and my undergraduate's in chemical engineering, and if you ever seen engineering paper, it's that lime green paper. It's a graph paper. I tend to do it this way because it makes it nice and neat and even. So by this, I mean 1.76 yards times meter to 1.094 yards times 100 centimeters to a meter. I tend to do the grid rather than the multiplication table. So, and if you notice the units here, yards cancel, meters cancel, and you're left with the units of centimeters. And centimeters, this would be 160.9 centimeters. So, and another way, the way I would do it if I didn't have the book in front of me, this is the way I would do it. 1.76 yards, so 3 feet in a yard, 12 inches in a foot, 2.54 centimeters in an inch. And 2.54 centimeters in an inch is an exact number. So we define inches by the metric system. So, but notice yards cancel, feet cancel, inch cancels, it's centimeters. So, and these are all exact numbers as well. These do not have. Wait a second. Oh shoot, it's 3 sig figs. I'm sorry. Sorry guys, I'm really off today. This is 161 centimeters. Is it someone? Yeah. I'm sorry about that. I just caught that. 1.76 yards, there's 3 sig figs. Okay. So that's another way you can do it. So, which also shows you there's more than one way to solve a problem. You don't have to solve a problem the same way each time. As long as the units work out, you're probably doing it right. So, questions with this one? One more time, 1.8 quarts to cubic centimeters. So, what's the given information? We are given a volume, and we want to have it converted to units. Let me do I'll do it in a different color for this one. So, start off with our given information, and one of the easy ways to do this is if you start off with what's on your left, and you get to what you need on the right. That is, then you usually know you're doing something right. So then the next, so we start off with this, and we're going to make our grid. 1.8 quarts, 1 liter is 1.057 quarts, and I would normally skip this step. The book is doing this a really weird way. Okay. What the book did, I'm looking at the book. The book did in this step here, put 1 milliliter to 10 to the minus 3 liters. I'd rather multiply than divide. I just like multiplying better than dividing myself. I don't know. But anyways, so doing this problem. So the quarts cancel, the liters cancel, the milliliters cancel, and we're left with cubic centimeters. So our answer here to 2 sig figs is 1,702.93. And how many sig figs? We have 2 sig figs. So the 1.8 is 2 sig figs. So put our answer in scientific notation, 1.7 times 10 to the third cubic centimeters. Okay, so a couple things with this problem. The book did it that way. I would do it this way. It's whatever your preference is. If you like dividing better than multiplying, by all means. So it means the same thing. And then here in scientific notation, if you leave the trailing zeros, your answer is ambiguous. This is considered the better way. So let me go back and explain the problem solving again. So recap. Problem solving, so sort, look at your given information, where you're going, strategize, figure out how you're going to solve the problem, and then check. Oh, and I even skipped that step, check. So, so for the first one here, we got the conversions. You look in the book at the conversion between meters and yards, or you can do it the way I would do it without the book. I would convert the feet and inches, and the fact that I know that 2.54 centimeters is an inch. And then we get our answer to 161 centimeters. I know it's small, but so let's think about this. Is 161 centimeters, is that about 1.76 yards? So in my mind, I know that a yard is about this long and a meter is about this long. A meter is slightly longer than a yard. I think a meter is about 39 inches and a yard is 36 inches. So in my mind, I think, okay, a yard is about the same as a meter, but a meter is slightly longer. So given that it's 1.76 yards, it's going to be about the same number of meters, but a little less. 161 centimeters is 1.6 meters, so that makes sense. So that's my check. This does make sense. And for this one here, 1.8 quarts. So I know a quart is about the same size as a liter, but a liter is slightly bigger, ever so slightly bigger. So I should get an answer about the same in liters. And I get, so 1.7 times 10 to the third, so that's 1.7 liters, 1,700 cubic centimeters. That's 1.7 liters. That's about the same as 1.8 quarts, but since a liter is slightly bigger, this makes sense. So that's kind of the thing you should think about when you're going through. So let's say I get an answer, I get 17 million cubic centimeters. Like, okay, next problem. Like, wait a second, 17 million, that's like something the size of this room. So I'm starting off with something twice the size of my water bottle, and I get an answer twice as big as this room. I did a calculation wrong. Let me check my calculations to see what I messed up. So that's the check step. So, questions with this? Nope. Okay. You guys look less than thrilled. The first third of the semester is kind of tough. So it's a lot of kind of boring math. And I think chemistry gets fun. Actually, chapter 7, chapter 8. That's quantum mechanics. I get excited about that stuff. That's the fun stuff. You're like, why is this guy a chemist? It's because, number one, I got to play with lasers. Number two, the way things bond and the way they interact. That's fun. I think this is boring. It's very important, though. Very important, boring stuff. Okay, now that we've done unit conversions, ever so fun unit conversions, let's do unit conversions that involve powers. So what is the displacement of a 5.7 liter engine in cubic inches? So 5.7 liters. So 5.7 liters is where we start off. And the book is doing the same thing. 1,000 milliliters to a liter. Okay. So a couple things for me. I'd probably skip this step right here. So a cubic centimeter, so centimeters cubed, also called a cc. Like if you ever look at those like shows like ER, give me 10 cc's of this stat, you know. A cc is a cubic centimeter is a milliliter. They're all the same thing. I'd probably just incorporate it in this step here and just say liter to centimeters cubed right there. So I would just entirely skip that step. But that's me. It's however you think and whatever works best for you. Now, if you look at the units though, if you go for the units, liters cancel, milliliters cancel, how do we get to this step here? You have to take this whole thing and cube it to get rid of the cubic centimeters. So you have to have that part cubed. So it's not divided by 2.54, it's divided by 2.54 cubed. So when you put this in your calculator, you've got to do 5.7, so times 1,000 divided by 2.54 cubed. Or if you want to do it, if you have to do it, you don't have a cube button, divided by 2.54 divided by 2.54 divided by 2.54. So if you put that in your calculator, that will give you the right answer. Or if you want, you can divide it by the quantity 2.54 times 2.54 times 2.54, close parentheses. Let's say for this, in this case, that you didn't put this parentheses right here. So if you did it like the one on the bottom, so your calculator only can do what you tell it to do. It's not an AI. Okay, it's a user digital interface. You're the user. If you put this into your calculator, and this is a very common mistake, what the calculator does, okay, order of operations left to right, it's 5.7 times 1,000. This is 5,700 divided by 2.54. That's about 2,500 divided by 2.54. That's about 10 divided by 2.54. That's about 4. Is that the right answer? No, that's too many. I'm not doing my math in my head right. Oh, it's 400. I'm off by a factor of 100. Where am I off by a factor? Anyways. So, but if you do it this way, you do this step, you divide by 2.54, then this number you multiply by 2.54. Then you multiply by 2.54 again. It goes from left to right. So you're going to get an answer much bigger than what you originally wanted. And the answer here is 348 inches cubed. So, I'm sorry to go in painstakingly detail on this, but I think this will save you mistakes later on in the future. To recognize what you put in your calculator is your calculator can only do what you tell it to do. So questions with this one? All right, so mass of jet fuel in a jet must be calculated to ensure the flight is not too heavy. So a 747 is fueled with 173,231 liters of jet fuel. The density of fuel is 0.768 grams per cubic centimeters. What is the mass of the fuel in kilograms? It's a lot of fuel. Okay. So now we're starting off small. We're increasing our level of difficulty, and the other ones are pretty easy. These ones are getting harder. So when I think about this problem, the first thing I'm going to do is I'm going to write what I know on the left. 173,231 liters. And I kind of look at this number here, and I'm thinking about it. I'm like, okay, how the heck do I get to kilograms? So I would do it differently than the book does it. So this is the way the book does it. The way the book does it is like so. So it has 1,000 milliliters to a liter, and then centimeters cubed to milliliter. Then we have so 0.768 grams per cubic centimeter. And if you want to know if you should multiply or divide that step, so if you're looking at the 0.76, do I multiply or divide by 0.76? Go by the units. So meaning for this step, do I divide or multiply by the density? I need to get rid of cc's, the cubic centimeters. I need to get rid of that. So how do I get rid of the cubic centimeters? It needs to be on the bottom. So I'm going to multiply by that term. And then, wait, that's backwards. Last step is kilogram to 1,000 grams. So you need to have kilograms. Look at this. The units all work out. Liters cancel, milliliters cancel, cc's cancel, grams cancel, and we're left with an answer in kilograms. So what's also nice about this, and when you put the numbers in your calculator, you're multiplying by 1,000, dividing by 1,000. You can just completely ignore the 1,000 then. Just don't even put it in your calculator. And then just do 173,231 times 0.768 and be done with it. And if you do that, the 3 sig figs is 1.33 times 10 to the 5th kilograms. That's a lot, 13,000 kilograms. That's 13 metric tons of fuel. Huh. That's a lot of fuel. All right, so recap. Let's look at this one. So we have 173,231 liters of fuel. What's the mass in kilograms? We know the density is 0.768 grams. So I look at this and I'm like, okay, well, a liter of fuel, so a liter of water is a kilogram. So that's what it used to be known as. But I guess a student told me that they changed the definition of kilogram to something involving voltage. So I guess they go by inertia now rather than mass. But that's fine. It should be the same thing. But okay, so we have this much fuel, and we want to know the mass in kilograms. So I know a liter of water is a kilogram. And so if this was water, it would be 173 kilograms. No, liters. I'm sorry, it would be 173,000 kilograms. So it would be 173 tons of water, but our density is about 3/4. So I'd be looking at, so whatever 3/4, 173 is, that's going to be around 140,000 tons, 150,000 tons, in that range, and 133,000 tons, 133,000 kilograms, 133 tons. So, questions with this one? All right, last one. And then we can go talk about atoms. So what is the radius in centimeters of spherical water droplet? Volume of the sphere is 0.058 cubic centimeters. And this is my own personal preference. I like to do all the algebra first. So volume is equal to 4/3 pi r cubed, and one's radius. So if we know we know what now this is, we have an equation, and we have one known, and we have to solve the equation. So the slow way to do this, and if you need to do this way, please by all means do it. You would divide both sides by volume, and you get 1 equals 4/3 pi r cubed. Oh, actually, no, we got to solve for r. Sorry. So we need to divide both sides by 4/3 pi, and we get volume over 4/3 pi equals r cubed. And then we would then raise this to the 1/3 power. So we get volume over 4/3 pi to the 1/3 power equals r. And then if you want to, then you can rearrange it to 3v over 4 pi cube root is r. So that's kind of step-by-step way. In my mind, I can take this and I see the 3 coming here, the 4 going there, the pi over there, and then taking the whole thing to the 3rd power. So I kind of see it. I see it doing this. You go like, it's fun to do math this way. Divided, divided, and then I mean, you can, if you, I mean, I know everyone kind of does math differently in his or her head, but I would just kind of plug it out in one step like that. So, however it works best for you. So let's put the numbers in now. So we solve the equation first. And we have radius is 3 volume over 4 pi. You can write it one way, the cubed root. That's one of the ways you can do it, and some calculators have that function. If your calculator doesn't have that function, you can use this caret and then do 1 divided by 3 in parentheses. You can also do the caret in 0.3333333 like that. So those are other ways you can do it in your calculator if you don't have the cube root, because a lot of times you have to like hunt for the cube root function in your calculator. So I do it that way. So then you plug in your numbers. So 3 in the volume is 0.058 centimeters cubed divided by 4 times. And your calculator can also have the pi button. Depends on how many numbers you want to put it in there. Like 3.14159, whatever you want to put in there for pi. Raise that to the 1/3 power. And then you get 2 sig fig 0.24 centimeters. And with the units, centimeters cubed, 1 cube root of cube is the base unit. So Again, sorry for all the painstaking detail of the problem solving, but hopefully this will save you mistakes in the future. For equations, my own personal preference is do the algebra first. Why do the algebra first? Because the most common mistake, well, besides algebra of operations, is putting numbers in calculator wrong. So you put the wrong number in. And later on in chapter 4, chapter 3 and chapter 4, we'll start to do calculations in class, so then you can practice putting numbers in your calculator. But I've noticed, at least for me personally, the more times that I put numbers in the calculator and carry numbers over, the more often I make mistakes. So that's why I do all the calculations at the end. So that way that's when I'm like, oh, this doesn't make sense. Where did I screw up? So you can look at your mistake in one step rather than 10 steps. So for this one, so let's say we did the other way around. I would be calculating 4/3 pi and get that number, then divide it by the volume, and then I would take that number and then I would take it to the third power. So that's what I would do if I didn't do the algebra first. And that involves putting numbers in my calculator 3 times versus 1. So both ways are valid though. It's however you want to do it. If you like putting numbers in the calculator 3 times and that's the way that you're sticking to it, that is totally fine. Go ahead and do it that way. But I'm just telling you my personal preference. So, questions with this one? Okay, good. Done with at least that starting out, and we're going to go on to chapter 2, as promised. So, atoms and elements. So, you may take this for granted, but I mean, it's more or less, occasionally, I think I've only met 3 people that had never heard of atoms, and one person was at a party after several rounds of consumption, and I think he just wanted to argue with me. So, he said, I don't believe in atoms. Atoms don't exist. And I was like, wow, this is my time to shine. I teach this stuff. So let me tell you, you've ever heard of the law of conservation of mass? So this now we take it for granted. We were like, okay, of course things are made of atoms. Everyone knows things are made of atoms, right? But this was a really hard sell a long time ago because you couldn't see them. I mean, atoms. We can see them. There's 2 ways to see them. One way is by using an SEM STM scanning tunneling microscope, or an AFM atomic force microscope. So this one is an STM, and this is probably an ATM. AFM, sorry. Atomic force microscope. This is probably a scanning tunneling microscope. So how's a scanning tunneling microscope work? So this image here. So let's say you have an atom. So my water bottle is an atom, and you have a piece of tungsten, and this piece of tungsten goes back and forth like this across a surface. And you put a voltage on it, and as this is going, if there's an electron cloud here, there will be electron density go from the piece of tungsten to the surface, and then the surface is connected electronically from the piece of tungsten down here. So there is an open area, and when this is scanning, then there's going to be a signal as it goes over. And when you have an atom and you have a piece of tungsten, tungsten is usually, it's not going to be a straight line. It's more like a bunch of grapes. So imagine I'm holding a bunch of grapes, and as I'm moving this bunch of grapes towards it, the grapes on this side are going to start to see a signal here, and then it's going to pass over it with the main bunch, and then as it's passing, there's going to be signal coming there. And because of that, atoms look like pimples. So atoms are more or less spherical. Instead of a sphere on the surface, your image looks like this. It looks like a pimple. Because of that, the atoms are like bunches of grapes on the tip of the scanning tunneling microscope. So this is a scanning tunneling microscope. This could be one. This is probably atomic force microscope, though. The way an AFM, atomic force microscope, works is you have a tip. So the tip looks like this. And then same idea, this scans over the surface. And if you have to have a really sharp tip, you can get atomic resolution. It's really hard to do, though. It's really hard to get atomic resolution for both scanning tunneling microscopes and atomic force microscopes. But if you have this tip that's shaped like this, and it moves over, and on a surface, it's going to be bumpy. It kind of bumps up and down as it moves back and forth. You have a laser that shines. So here's a tip. You have a laser that shines on the tip, hits it off, and has a detector. And then that detector looks at little perturbations in that signal. And with an AFM, atomic force microscope, because it bumps up and down, hits an atom, and chinks up like that, they look like candy corn. So an atomic force microscope, the atoms, a lot of times, they look like you see this sharp candy corn shape. And that's because the signal is from a laser, and when it hits the atom, it bumps up. So you see a spike in the laser, and it comes down. So when it does the image, you see like these, looks like an atom looks like, at a field of atoms, like a bunch of like candy corn sticking upside down, which is what you see here. So, but the images are very close for an atomic force microscope and a scanning tunneling microscope. So anyways, so we can see atoms, right? We can image them at least. Back in the 1850s, though, we couldn't. And the originators of the atomic theory really belong to the Greeks. So good old Greek philosophers. They thought that there were 4 elements: earth, wind, fire, water, and they were made of tiny indestructible spheres called atoms. And the Greeks were really confused. So the idea, though, was that earth and water were like gravity. They were like heavy elements, and fire and air were like anti-gravity. They're like light elements. And they were forever confused because if you took a piece of wood and you burned it, when you burn wood, you can get water out of it. We know that combustion forms H2O water. So you can condense water from stuff coming from wood. But the ash that was left over was lighter than the stuff that you, like if you took the mass of the wood plus the mass of the water, the mass of the wood, you weighed that, and you took the ash and then water where you could reclaim, you had some missing mass here. And the Greeks were really confused about this. But then if you took mercury, like the metal mercury, and you burn that, you get cinnabar, that's heavier. So why is it that I take something like a piece of wood, I burn it, and it's lighter, then I take mercury and I burn it, and it's heavier? So that was one of those, we don't know what's going on. It must be the God's fault or something, that kind of thing. So the best they could come up with was, well, there's that fire and air are anti-gravity, and earth and water are gravity, because you can take ash, you can burn it more. If you heat it up high enough, you can burn it, it goes away. So, there was still fire in that, but now it's nothing. So, but the Greeks were confused about that, and there was something wrong. But Dalton came along, so Dalton's atomic theory. He came along and he built it off of these 3 laws: law of conservation of mass, law of definite proportions, law of multiple proportions. Conservation of mass, matter is not created or destroyed. Definite proportions, for compounds, elements, for a compound, the elements are the same in each compound in the same proportions. So if we have water is going to be, so it's 18, so it's going to be 1 gram oxygen, 1 gram hydrogen to 8 grams of, 1 gram of hydrogen to 8 grams of oxygen. So it's 1/9 hydrogen and 8/9 oxygen for water. Always true. Then we have the law of multiple proportions. If you have two or more elements, you can form different compounds, but in different ratios. So they noted that for compounds, there are always set ratios, but for different elements, they could figure out things are made of elements. You can take two elements, you can get different ratios, or you can get different compounds from them, but they still have the rule of definite proportions work. They're going to be in different ratios. So hydrogen and oxygen, we can form water, and we can form hydrogen peroxide with that. So the difference is that water is 1 to 8, hydrogen to oxygen, and then hydrogen peroxide is 1 to 16. So H2O2 for peroxide versus H2O for water. So 1 to 1 versus, well, atomic 1 to 1 by mass, 1 to 8 versus 1 to 16. And showing here, here's the law of multiple proportions. For carbon and oxygen, we can form two different compounds. We can form carbon dioxide, and we can form carbon monoxide, but they have two different set ratios. So carbon monoxide being 1 gram of carbon to 1.33 grams of oxygen, that's the law of so definite proportions. And the fact that we can form two compounds of different ratios, that's the law of multiple proportions. And the ratios are set. So, and so then Dalton came and had his atomic theory. Oh, and here's an illustration of the law of conservation of mass. So if we have 7.7 grams of sodium and 11.9 grams of chlorine, we can react that to form 19.6 grams of sodium chloride. So we start off with 19.6 grams, and we get 19.6 grams. So that's sodium chloride salt. And so low budget, we have, is that going to be chlorine, or is it going to, yeah, it's chlorine. So here's Theodore. Here's chlorine, sodium. So that's chlorine gas. Now he's
Everyone back.
This guy's insane,
Okay.
by the way.
Round 2.
That's some eggs or something there. So that's how he's putting salt on his food. So this guy, Theodore Gray, it's his periodic table on the back here. He's crazy. I've never met him. I've read some of his books, but he likes to throw sodium parties at his house. Here's sodium here. Oh, whoops. He likes to dump sodium. He invites people over his house, and he has, like I said, sodium parties. So he's like the mad scientist of today. Okay, so here's the law of conservation of mass. And the law of conservation of mass, quick story, this was discovered, I guess it always was there, more heavily characterized by Lavoisier. He was a French nobleman. I think the noblemen in the 18th and 19th centuries were really bored. So he and his wife, I don't know how you flirt with your significant other, but they met at a party, and he was doing an experiment. He said, you know what? If I just drink milk, I can sustain myself for a long time. So he would do nothing but drink milk, and I guess it was a crazy diet back then. Still would be a crazy diet now. But his wife like, what you doing? He's like, oh, I'm just seeing if I just drink milk, I can get all the nutrition I need. And he was experimenting on that, and she thought it was cool, and she was a scientist too. And then they started doing experiments together. And they found out that for any physical or chemical process, if they were very careful about how they weighed, and if they did something like, say you take something like baking soda and vinegar, that formed the carbon dioxide gas.
if they collected the carbon dioxide gas and they took the mass of the baking soda and the vinegar, and then the liquid, there's going to be liquid sodium acetate in the bottom and in solution, then the carbon dioxide boils off. If they collect the carbon dioxide, something like stacked lime, so calcium hydroxide that's wet, if you run carbon dioxide through that, it'll absorb to form calcium carbonate. If they were very careful and they weighed everything, they found out like, oh, matter is not being destroyed or created. So they did this over and over and over again. That was their loving relationship, was kind of they played in the laboratory together. But they came up with the law of conservation of mass because of it. But so here's an illustration of that, but by using atomic theory. And the idea here is in a chemical reaction, atoms exchange places. They're not created or destroyed.
And that's what Dalton said. Dalton said here that each element is made of tiny indestructible particles called atoms. So this is wrong. They're not indestructible. All the atoms in the given element are the same, and other properties that distinguish them from their like all atoms of the given element are the same mass, and other properties that distinguish them from the other atoms and elements. This is also partially incorrect because we have something called isotopes. So that we have an element with the same number of protons but a different number of neutrons. Atoms combine in simple whole number ratios for compounds, and this fits with both the law of definite proportions and multiple proportions. And then atoms of one element cannot change atoms of another element. And that in a chemical reaction, only the atoms is exchanged. So, what Dalton really thought, it's kind of like the ball pit in McDonald's. Like you go to McDonald's and you go and jump in the ball pit. He thought atoms were like that. Like different colors are different elements, and they're just these tiny indestructible spheres. And they're all the same. But the blue atom is different. It's a different element than the red atom, kind of thing. And then then we disproved atomic theory, well, at least Dalton's atomic theory, because we could rip off electrons. So they found out that if you can make cathode rays by stripping electrons off of atoms. And I don't want to go through all the history. This is not a history class. But then came up with the plum pudding model of the atom. So the plum pudding model, this is, like what the heck is plum pudding? It'd be better if we called it the blueberry muffin model. So imagine a blueberry muffin is mostly muffin with some blueberries in there, right? So the idea is an atom is like this big sphere of positive charge with these electrons floating on the inside. So kind of like a big muffin with blueberries in it. So that's the plum pudding model. Of course, this is British, so I guess they didn't have blueberry muffins back then. Then, so in typical scientific fashion, we got two competing theories. We have the Dalton's model, and then we have the plum pudding model. Which one's right? So Rutherford came along, and this is also, I guess, sidestep. This is also how our smoke detectors work. So like your smoke detector at home, the way it works is you have a radioactive source. So at home you have americium as a little element. At least if you have a cheap smoke detector, this is how it works. You have a piece of americium in a box, and that americium is shooting radiation, and then you have a detector up here. If smoke goes through this beam of radiation, it ionizes, and then is detected, then the ions are detected by the detector. And then if the detector gets ions, and it goes off. That's why like steam from a shower sometimes will set off the alarm. Just if something goes through that beam of radiation and is ionized and is detected, the alarm sounds. So same idea, but Rutherford took an alpha source like uranium, and gold. You can take gold, you can hammer it into really, really thin sheets. So he put a piece of really thin gold, and then around all this put a phosphor screen. So mind you, this is like in the 1850s. I don't know the exact date, but it's like the middle of the 19th century. This is before computers. So what Rutherford did is he
he picked one of his grad students and gave the grad student one of those clickers. You ever gone to like Costco and sometimes there's someone there with a clicker and like, all right, click, 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 whenever you walk in the door. I mean, those are old technology. It doesn't take that much to, press a button as a spring that a number goes up. So he gave the student a clicker, and of course this has to be in the dark. And with a phosphorus screen, whenever a radiation hits it, it flashes. So Rutherford said, all right, what I want you to do is I want you to sit here in the dark, and I want you to stay here for half an hour, and then look to see how many flashes you see, and then after half an hour, go to the next spot, write it down, and then do it again, and do it again, and again, again, and do it all the way around. And then compile the data, give it to me, and let me know what you think. And what Rutherford was hoping to see, he would see one of two things. If it was the plum pudding model, all the radiation would just go right through. If it was Dalton's atomic theory, where atoms are these like indestructible spheres, the radiation would all be bounced off this way. Nothing would go through, all the radiation would be bounced off in the front. So the grad student did this, and what the grad student found out was most of the radiation went right through, but some of it deflected off the pattern. And then so the grad student compiled all the data, showed it to Rutherford, and he says, this is wrong, entirely wrong. Do it again. So the grad student spent another 2 weeks or something like that going through all this and compiled the data, showed it to Rutherford, and he says, you're still getting it wrong. Do it again. And the grad student's like, hey, look, professor, you're smoking your pipe in your tweed jacket, drinking coffee with your friends. I'm in the dark lab doing this. If you want to come and watch me do it, come and watch me do this. But I'm doing this correctly. I've done it twice already. And Rutherford was thinking, maybe that data is right. And this is what he was hoping to see, that the plum pudding model would go right through. But he thought, maybe instead of the plum pudding model being correct, instead of this really big, diffuse positive charge, what if we had a very heavy positive charge in the middle of the atom? And at this point in time, we figured that electrons were we called electrons negatively charged. So we have a really heavy positive charge in the center, and then we have a very diffuse negative charge on the outside where the electrons are. And that is the Rutherford atoms, the atomic atom. Right now, the current theory of the atom is the quantum mechanical model, which we will cover in Chapter 8. So it's much more complicated than this. But this is true. Rutherford's atomic atom is correct. Well, mostly. There's a better way of describing it, a better model. Okay. And so what? Well, we have subatomic particles. So subatomic means less than, sub is less than atomic particles, like a sprinkle is a sub-donut particle. So since I haven't been feeling well this weekend, I splurged and got some donuts at Krispy Kreme, right? And I did get a pink donut that had sprinkles on it. If I took one of the sprinkles off of it, that would be a sub-donut particle, right? So I can take an electron, a proton, a neutron off of an atom, and they're subatomic, they're less than atom particles. And here's their mass. So AMU is atomic mass units. Carbon-12 is said to have 12 AMUs. So it's relative to carbon-12 if you wonder where it comes from. And a couple things to note. A neutron is slightly more massive than a proton. And that is because if you let a neutron sit off by itself, it will undergo a process called beta decay, where it will shoot off an electron and become a proton and an electron. So neutrons are slightly more massive. They have no charge. Protons have a +1 charge, +1 being plus 1.6 times 10 to the minus 19 coulombs. 1 amp is a charge of coulomb per second. So, and an electron is negative 1.6 times 10 to the minus 19 coulombs. So, and then we get to elements. We define them as such. Normally, we just see them as the chemical symbol. So if we have an element and we talk about things in this nuclear sense, if we're looking at the atom's nucleus, so most frequently when you write something like carbon, so C2O, I'm sorry, CO2, jeez, carbon dioxide, CO2, you're saying carbon and 2 oxygens, you're not looking at the nucleus. The chemical symbol being carbon, we already know that carbon has 6 protons. So the atomic number is in the bottom. It's the same thing as the chemical symbol, because what defines an element are its number of protons. The top number is the mass number. It is the number of protons plus the number of neutrons. And elements are defined by the number of protons. So I'm sure this is the first time you've ever seen this before. This is the periodic table. And the periods, what does the periodic table mean? The period means the rows. This is the first period, this second period, third period, fourth, fifth, sixth, seventh period. So the periodic table. And something you might notice, it's a funny shape. First of all, it's a funny shape. Secondly, what is a stepladder? You have a stepladder there. What the heck is that? So the way the periodic table should be, it should be listed as such. It should look like this. That's the way the shape should be. But that shape is too long, and we like things that are in the golden ratio. So this iPad is about the golden ratio. This textbook, the length to width is about the golden ratio. My arms to my legs are at the golden ratio. We think it's a really pretty ratio. So what we do is we take this portion and we put it down here. Because that way it can fit on a piece of paper and it looks prettier. Okay, so the periodic table is this shape because we think it's prettier. So if you see the numbers, you have 57, then 58 goes down here. Like I say, it should be there, but we put it this way so it'll fit in the piece of paper better, which we think is beautiful. Okay, then we go to, if you look at a periodic table, here's a even prettier periodic table. So the step ladder is, right, I'm not that tall. Oh, jeez, there's a, okay. The step ladder starts over here with boron and it steps down all the way over here. To the right of the step ladder are known as nonmetals. To the left of the step ladder, including these, are known as metals. And then along the step ladder are known as metalloids or semiconductors. So semiconductor, sort of conductor. So metals tend to conduct heat and electricity very well. Nonmetals tend to be insulators. And I'm using the word tend on purpose because some nonmetals can conduct electricity and some are great conductors of heat. So carbon is weird. Carbon, graphite, the stuff in your pencils, is a conductor. That'll conduct electricity. And diamonds, I already mentioned this before, have the highest thermal conductivity that we know of. So diamonds conduct heat extremely well. But things like, I'd say non-metal, so this, not the plastic coating here, this is high density polyethylene. It's carbon and hydrogen, both non-metals. It does not conduct electricity very well. It's an insulator. So if let's say that this wall had 10,000 volts on it, if I were to take this say I took the electronics out and just had the case, if I lean the case up against the wall, would it shock me? No. My aluminum water bottle, would this shock me? Yes. This is aluminum. It's a metal. It conducts electricity very well. What about silicon? Here is silicon. Silicon is somewhere in between. It's kind of shiny. I mean, look at that. It's like here's ultra purified silicon.
It even reflects light. This is kind of like a metal, but if you look at this hunk here, look at that though. It's got like a crystal structure to it. It's like a shiny crystal. Is this a metal or a non-metal? It's kind of both. So silicon, if you look at silicon, it is the basis of our computer technology. So we work off of binary, 1 and a 0. We used to use vacuum tubes. So if when electricity, oh, that's my alarm. That's my shut up alarm telling me it's time to shut up. All right, shut up alarm is going off and class is over. We will see you guys then on Monday.